In this video we are going to talk about colligative properties. But first let's start with molality. That is a type of concentration that is independent of the temperature. As a formula is the number of moles of the solute divided by the mass of the solvent in kilograms. Molality is particularly useful when we need to compare concentration over a range of different temperatures. That's why we use it in the colligative properties. But what is a colligative property? It is a property that depends on the number of particles dissolved in solution, not on the type of the particles. In this video we will discuss 4 types of colligative properties that are vapor pressure lowering, freezing point depression, boiling point elevation and osmotic pressure. Let's start with vapor pressure. How does a non-volatile solute affect the vapor pressure of a liquid into which it dissolves? The basic answer to this question is that vapor pressure of a solution is lower than the vapor pressure of the pure solvent. But why? Because the nature has the tendency to mix, or in other words, toward greater entropy. That is the scale of disorder. Let's take a look at this scheme here. If we have a sealed container, as this one here, and we leave for a long time a pure solvent, a glass with a pure solvent and a glass with a concentrated solution that contains a non-volatile solute into it. Over time the level of pure solvent drops and the level of the solution rises. We can quantify vapor pressure of a solution with Raoult's law. That is, pressure of the solution is equal to mole fraction of the solvent multiplied by the pressure of the pure solvent. What is the mole fraction? Mole fraction is, in this case for the solvent, is the number of moles of the solvent divided by the number of moles of solvent plus number of moles of the solute. Mole fraction of the solvent plus mole fraction of the solute is equal to 1, so the maximum value that mole fraction can take is 1. Keep in mind this thing. And you can play with formulas and you can derive this formula. Let's move now to this example to better understand the vapor pressure lowering. Calculate the vapor pressure at 25 degrees Celsius of a solution that contains 100 grams of sucrose, a non-volatile and non-electrolyte, and 400 ml of water. The vapor pressure of the pure solvent at 25 degrees Celsius is 24 torr. Assume the density of water 1 gram per milliliter. First, by starting with the density, which means that is 1 gram per milliliter, so 400 milliliter of water is approximately 400 gram. So what we need to find? We need to find the mole fraction for the solvent in order to find the pressure of the solution. In this case is water, the solvent, is equal to number of moles of water divided by number of moles of water plus number of moles of the sucrose. So the mole fraction of water is equal to 0.98. Now we have the option to calculate the pressure of the solution. So if we calculate here, pressure of the solution is 23.52 torr. So is lower than 24 torr. It's not dramatically low, but is lower. Let's move now to the case that we are dealing with an electrolyte, non-volatile electrolyte. So in this case we have a solution that contains 0.1 mole of calcium nitrate, strong electrolyte and non-volatile, and 1 mole of water. Calculate the vapor pressure at 55 degrees Celsius. The vapor pressure of pure water at 55 degrees Celsius is 118 torr. Assume that the solute completely dissociates. So we need to find the pressure of the solution. But what is the difference between the non-electrolyte and electrolyte? We mentioned at the beginning that colligative properties depend on the number of particles, not on the type of the particle. So in this case, the number of particles that are going to be present in the solution, we are going to consider the dissociation of the salt. In this case, that is by assuming that it completely dissociates. So we are going to have So the number of particles in our solution is going to be one here and 2 here. The total 3. A total of 3 particles in the solution. So we know from the last example that the formula for the Raoult law is going to be pressure of the solution equal to mole fraction of the solvent multiplied by the pressure of the pure solvent, in this case is water. So when we are going to calculate the mole fraction for the water, that is a solvent, we are going to take in consideration 3 particles, not only 1 as a formula unit, because it's completely dissociated in the solution. What do we have? Number of moles of water divided by number of moles of the calcium nitrate multiply by 3, because we have 3 particles, plus number of moles of water. So it's going to be 90.77 torr. That is lower than 118 of the pure water and is more dramatic, the vapor pressure lowering if in case of electrolyte solutions. As you can see here, the triple point is shifted on the left. So this one here was here, it's going to be here in the solution. So as a result, it gives us a lower freezing point for the solution and a higher boiling point for the solution compared to the pure solvent. The typical real-life example of this one is in automobile antifreeze. That not only prevent the freezing point of the water, but also prevent the boiling point of the water. The amount that freezing point decrease and the boiling point elevate is given by the following equation. We have change in the freezing point that is equal to the I, that is a Van Hoff factor that I'm gonna explain in a second. It has the constant of freezing point and molality in italic. Molality, because as I mentioned at the beginning of this video, molality does not depend on the temperature, but molarity depends on the temperature. The same change in the boiling point is equal to Van Hoff factor that I'm going to explain in a moment, and the Kb, that is the coefficient that for the boiling point, and the molality. What is I, that is Van Hoff factor, is number of particles in the solution divided by the number of formula unit dissolved. I for non-electrolyte is going to be 1, because they do not dissociate in the particles. I for the weak electrolyte is going to be higher than 1, not too much, but a little bit higher than 1. And I for the strong electrolyte is going to be the number of ions in the solution that are present. In this case, sodium chloride, for example, it dissociates completely in sodium plus and chloride minus. So the I is going to be theoretically equal to 2. Experimentally, it's observed an I equal to 1.9. The reason that Van Hoff factor does not exactly correlate expected value is that some ions effectively pair in the solution. This scheme demonstrates that normally the sodium and chlorine ions are hydrated in the solution, but at some sort of probability they are closer to each other, so they pair. And that's why the Van Hoff factor is slightly lower. And this trend, if we have more particles for the same formula unit, is gonna go lower, the Van Hoff factor. But these are tabulated values that can be found on general chemistry books, so you don't need to remind. But you have to remind that number of particles is going to give us the Van Hoff factor that is going to be taken in consideration for electrolyte solution. Let's move now straight to an exercise that deals with boiling point elevation and freezing point depression for a non-electrolyte case first. A glucose solution contains 60 grams of glucose in 500 grams of water. Determine the freezing point and the boiling. I have confused something here, but don't worry. Determine the freezing point and boiling point of a solution. This is given the Kf 1.86 degrees Celsius per molality and Kb 0.512 degrees Celsius per molality. So what we are going to find first? First we are going to find Van Hoff factor. That is I for a non-electrolyte like glucose is going to be equal to 1. We know the change in the freezing point is going to be equal to I multiplied by Kf multiplied by molality in italic. Do we have molality now here? Not, we do not have it. So we are going to calculate first the molality. So the molality of this solution is going to be equal to number of moles of the solute, that in this case is number of moles of the sugar, divided by the mass in kilogram of the solvent, that is in this case is the water. Mole per kilogram, or 0.66 molar. Now we have the option to find the freezing point, so it's going to be so this is the change in the freezing point. So the freezing point itself is going to be the freezing point, the temperature of the freezing point for the pure water minus change in the freezing point, and it's going to be equal to 0 minus 1.23 degrees Celsius minus 1.23, and the boiling point Let's move now to a case that considers a strong electrolyte. Calculate the freezing point and boiling point of 10 grams of iron chloride trivalent and in 100 grams of water. Assume complete dissociation of the solute. So first we have to determine the Van Hoff factor, that is equal. How many particles do we have? This salt dissociate iron 3 plus 3 chlorine minus. So it's going to be 1 here and 3 here, 4. Approximately 4, because in reality it's going to be around 3.4. But we are going to count it as 4, because the exercise said us that assume complete dissociation of the solute. So what we are going to find first? So the decrease in the freezing point is going to be minus 4.53 degrees Celsius. If we calculate this here, it's going to be 0.61 molar, 1.25 degrees Celsius. Theoretically are these values, practically are slightly lower. Let's move now to osmotic pressure. But first, what is osmosis? We need to understand osmosis in order to understand osmotic pressure. Osmosis is the flow of the solvent from a solution with lower solute concentration to the one with higher solute concentration. As you can see on this scheme, on this side we have a solution. On this side we have pure water. Over time, water levels rise on the side of the solution and decrease on the side of the pure water. In this case, in order to prevent this process, we have to apply a pressure on this side. If this pressure is sufficient to stop osmosis, we say that this is the osmotic pressure. But as you can see here, we can also apply more pressure than to stop osmosis, and we can, for example, desalinate the water from the sea and reverse the process. On paper it looks easy, but in reality it's an expensive procedure. It's done in some parts of US countries that they need for drinking water, but it's a really expensive process because the pressure that you have to apply here to reverse osmosis is too high. One thing that changed at this colligative property, in this case we are going to use molarity, okay? Not molality in the osmotic pressure. Osmotic pressure is measured with atmosphere. We also have here Van Hoff factor, molality, that is mole per liter. We have the gaseous constant, that is liter atmosphere per Kelvin per mole, and the temperature is going to be on Kelvin, okay? This is the formula to calculate the osmotic pressure. Let's move to an example to calculate the osmotic pressure. Okay, calculate the osmotic pressure of 10 grams of sodium chloride in 500 milliliters of water at 25 degrees Celsius. So what do we have? Again, sodium chloride. We are going to assume the complete dissociation is going to be sodium plus chloride minus. So the number of particles is going to be 2. That is I, the Van Hoff factor. We know that osmotic pressure is I multiplied by molality multiplied by R multiplied by T. Temperature is at 25 degrees Celsius plus 273 Kelvin is going to be what? 298 Kelvin. So we found the temperature. R, we know that 0.0 is no need to remember it. You can open general chemistry book and you can find that there. 0. Or ask the best friend that we have, Google, and you can find that easily. 0.0821 liter atmosphere per Kelvin per mole. What we need to find here? We need to find the molarity of the solution. So molarity is going to be equal what? Number of moles divided by the volume of the solution. In this case, what do we have? Number of moles is so molarity is 0.35 mole per liter. From here we can find the osmotic pressure. As you can see, the pressure is so high even to stop the osmosis of 10 grams of sodium chloride. That's why I said before that doing the reverse osmosis is cool and is in our interest, but the energy that you need to spend to reach such kind of pressures is costly. That's why it's not a preferable process. Another useful application that has osmotic pressure is to find the molar mass of a compound. Because it's so sensitive, even in lower amount of solute, let's see this example to demonstrate that effect. A solution contains 30 milligrams of unknown protein. Proteins are non-electrolyte. Per 30 milliliter of solution was found to have an osmotic pressure of 4.3 torr at 25 degrees Celsius. What is the molar mass of the protein? So first, I is equal to 1, non-electrolyte for proteins. So we need to find the molar mass. First, we have osmotic pressure, we have the volume, we have the temperature, we have the mass of the protein. We know that molar mass is gram per mole. Okay? So we need to find first the number of moles, because the number of grams is given, and we can convert this even here immediately in grams, because it's in milligrams. It's going to be 1 gram over 1000 milligram. 3.10 to minus 2 gram. We need to find number of moles, but before finding number of moles, we need to find the molarity of the solution. So from this formula, we can find the molarity, that is P. So the molarity of the solution is going to be equal to what? P, or osmotic pressure, has to be converted into atmosphere. But we know that molarity itself is number of moles per liter of the solution. So here we can find number of moles of the protein that is contained on this volume of the solution that is given here. So number of moles is going to be, so we have 30 milliliter of the solution, so it's going to be, and we found the number of moles. We have the number of grams of the protein, we found the number of moles, and we can find, by dividing them, we can find the molar mass. So the molar mass is 4,329 grams per mole. You know that the proteins have a way higher molar mass. Alright, thank you so much for watching, guys, and see you in the next video. Hope this video was a little bit helpful to understand the colligative properties. Thank you so much again for watching, and see you in the next video. Peace.